Uh, Good morning to one and all. And we are going to see the topic on ketone bodies. So, ketone bodies is what is ketone body? Ketone bodies are nothing but just metabolic products that are produced in excess during the excessive breakdown of the fatty acids. So, these fatty acids, these ketone bodies are nothing but acetoacetate, acetone, and beta hydroxybutyrate, which is collectively known as ketone bodies or acetone bodies. The acetoacetate and acetones are the two true ketones, while beta hydroxybutyrate does not possess keto groups. So it is very important source of energy for the peripheral tissues. Why? How? It's because they are insoluble in aqueous. So they don't need to be incorporated into lipoprotein or carried by the albumin like lipids. Okay, that is why these ketone bodies are important source of energies. They are produced in liver during a periods when acetyl-CoA present exceeds when the oxidative capacity of the liver. They are used in the proportion to their concentration in the blood by extrahepatic tissues. It's like skeletal, cardiac muscles, and renal cortex. Mainly, brain, heart, and muscle can use ketone bodies to meet their energy needs if the blood level rise sufficiently, particularly during the prolonged fasting conditions. So, why ketone bodies are synthesized by the liver? Because ketone bodies from the liver to the hepatic tissues are allowed to continued by the oxidation of fatty acids in the liver. When acetyl CoA is not being oxidized in the citric acid cycle. So that is why they are synthesized by the liver. Okay. So how they are synthesized in the liver? We have a four different steps which is involved in the synthesis of ketone bodies. First is synthesis of acetyl-CoA. So this can be taken place by two-step process. That is by when there is an incomplete breakdown of free fatty acids and when the enzymatic condensation of two molecules of acetyl-CoA occurs, which is catalyzed by the enzyme HMG which is catalyzed by the enzyme thiolase. So, which is the reversal reaction of fatty acid oxidation. Next is acetoacetyl-CoA condense with the third molecule of acetyl-CoA to form HMG-CoA, which is catalyzed by the enzyme HMG-CoA synthase. So, this HMG-CoA helps in cleaving free acetoacetate and acetyl-CoA by the enzyme HMG-CoA lyase. So lyase helps to cleave. So it is lyase. The enzyme means it is lytic function. So that is ligation. It is splitting up. So it splits up the acetoacetate and acetyl-CoA in component. This acetoacetate, which is free form, is reversibly reduced by beta hydroxybutyrate dehydrogenase with the help of NADH, which is an hydrogen donor, so that beta hydroxybutyrate can accept the hydrogen component. So the acetoacetate, uh, so which can this beta hydroxybutyrate, or it can be spontaneously decarboxylated to form a acetone. So the other form component of ketone bodies. So beta hydroxybutyrate dehydrogenase main enzyme which is involved. This enzyme specific for in the mitochondria. Okay. So how the ketone bodies are utilized by your peripheral tissues? So it occurs in four formations when there is a low level of ketone bodies. So liver produce a low level of ketone bodies, but this production is increased when there is a more significant during the starvation condition. It is increased during the starvation condition, which when the ketone bodies are needed to provide energy to the peripheral tissues. That time these ketone bodies are come into act. So liver actively produces ketone body, but it can't utilize it as a fuel. It as a fuel because it cannot reconvert the acetoacetate to acetyl-CoA. So these component cannot reconvert the acetoacetate to acetyl. They can be they cannot be utilized as a fuel. So they can be utilized as a regulator. So in case of in extrahepatic tissues, these acetoacetate is activated. So the acetoacetate which is get activated through acetoacetyl-CoA by succinyl-CoA acetoacetate-CoA transferase, because this transferase component helps to transfer CoA from the succinyl to acetoacetate. That is why it forms the acetoacetyl-CoA. So in extrahepatic tissue, including your brain, heart, and muscles, can efficiently oxidize these type of acetoacetate and 3-butahydroxybutyrate. This how these ketone bodies are utilized. First, 3-hydroxybutyrate is oxidized to acetoacetate by 3-hydroxybutyrate dehydrogenase by producing NADH. The acetoacetate receives a coenzyme A from succinyl-CoA by the action of the enzyme transfers, because which is present only in the liver, present in all the tissues except the liver. This enzyme is present in all the tissue except in the liver. Okay, so its absence allows the liver to produce ketone bodies, but do not utilize them. This ensures that extrahepatic tissue have access to ketone body as a fuel source during a prolonged fasting and starvation. So acetyl-acetyl-CoA is actively removed by its conversion to two molecules of acetyl-CoA by the action of lyolase. So ketogenesis is regulated by three steps. So three steps is regulate partition of acetyl-CoA between the pathway of ketogenesis and the citric acid cycles. So this condition occurs when there is a decrease in the concentration of oxaloacetate within the mitochondria, because citric acid cycle is initiated with the oxaloacetate in combination with your acetyl-CoA, and it forms your citrulline. Okay, so this is the first step. So this concentration, when there is a decrease in the concentration of oxaloacetate within the mitochondria, it impairs the ability of the citric acid cycle to metabolize the acetyl-CoA and divert the fatty acid oxidation towards your ketogenesis. So such fall when this acetyl-CoA, that is oxaloacetate reduction will occur when there is a increase in the NADH ratio. So by which increases the beta oxidation, which uh, consequently affects the equilibrium between the oxaloacetate and the malate and decreases the concentration of oxaloacetate. So next is the free fatty acid mobilization from adipose tissue directly affects the level of ketogenesis. This is the main factor which is regulating the mobilization of free fatty acids from adipose tissue, and which is the main important controlling steps of ketogenesis. Next is carnitine palmitate transferase 1, the activity of carnitine, which is present in the liver, which determines the proportion of fatty acid flux that is oxidized rather than esterified. And carnitine palmitate transferase is one of the main regulatory enzyme in the beta oxidation, which regulates the fatty acid into the oxidative pathway in the mitochondria. And this, when there is a low in the fed state of CPT, which leads to the decrease in the fatty acid oxidation, and this occurs in the high in the starvation, which allows the fatty acid oxidation to increase. Simultaneously, malonyl-CoA, the initial intermediate in the fatty acid biosynthesis formed by acetyl-CoA carboxylase in the fed state, is a potent inhibitor of the CPT1. So this is the main inhibitor of the CPT1. This will lead to decrease the entry of fatty acids, the mitochondria, and all esterified to acylglycerol, which proportionally decreases the production of acetyl-CoA. So CPT1 is high in starvation, so allows the fatty acid oxidation to increase, As the concentration of fatty acid increases with the onset of starvation, acetyl-CoA carboxylase is inhibited and malonyl-CoA decreases, and CPT1 transports more acyl-CoA to mitochondria to be oxidized, which increases the production of acetyl-CoA. This event is reinforced in the starvation of decrease in the insulin or glucagon ratio. Thus, beta oxidation is which is the main controlling regulator of beta oxidation is CPT1, which is the gateway into the mitochondria, and this helps in balancing your free fatty acid uptake, not oxidized in the esterified form. So, this is what your biosynthesis of ketone bodies and how it gets regulated by the three different crucial steps. Three important crucial steps which helps in the regulating the keto bodies synthesis. Thank you.